Hi, I am Mirhan and I'm going to be presenting our joint paper with Professor Işıl Bozma, which deals with 3D pointing direction estimation. In the paper, we address the detection of 3D hand pointing direction by mobile robots. Pointing direction estimation improves human-robot communication with possible applications in areas like human-guided object learning and environmental modeling. In our model, only the hand data is used to estimate the direction, although other parts of the body may give some useful insights, such as alignment of the head. This is mainly because robot may not be able to see the whole body in all cases. To this end, a three-step algorithm is developed. Differing from previous work, the robot is able to estimate the 3D hand direction, both accurately and fast, regardless of the proximity, background variability, or the detectability of specific human parts. We also present a sensitivity analysis of the final estimation to the sensor noise. Two new datasets for pointing gesture classification and continuous 3D pointing direction are made publicly available, as there are no such datasets to the best of our knowledge. Here is a table summarizing related literature about pointing direction estimation. Applicability of these methods in robotic applications depends on several issues as listed here. It can be seen that our approach is the first 3D pointing direction estimation method with the least amount of assumptions, to the best of our knowledge. We do not have assumptions about the background or do not require hand to be close to the camera, etc. We are using RGB-D data coming from a Kinect sensor. Using this data, first, a novel sequential network-based learning model is developed for the simultaneous detection of hands and humans in RGB data. Then, hand regions are labeled as pointing or non-pointing by a CNN-based classifier. Following a density-based algorithm, segmentation algorithm is applied to the pointing hand regions to get the 3D hand segment. A new geometric method for estimating the 3D pointing direction from depth data of the detected hand is then applied to get the final estimation. Direction estimation starts with finding hand and human regions from RGB image. We use CNN-based state-of-art yellow version 4 architecture for this job. To train the architecture, a dataset with both human and hand labels is required. However, there were no such dataset in the literature. So we first created a hand and human dataset and trained yellow version 4 to get the final detector. This is achieved in 3 stages. First, a hand detector is created by training the network on the Coco hand dataset. Next, the hand detector is run on the human images of Coco dataset as to create an annotated dataset with hand and human labels. This dataset is then used to train the network once more, hence the network learns to detect both hands and human. After finding hand bounding box, robot needs to determine if the hand is performing a pointing gesture to avoid non-pointing hands to be processed further. To this end, we trained a convolutional neural network with our own dataset consisting of pointing and non-pointing hand regions. We tried to include images with varying conditions such as illuminations and hand distance to the camera. The architecture of the CNN is given in the figure, which is inspired by another pointing gesture paper, and it is similar to the AlexNet architecture, which is quite popular in the literature. If a hand is performing a pointing gesture, hand bounding box region is mapped to 3D space using depth data. Then a density-based segmentation algorithm, which is an improved version of an existing one, is applied. Original algorithm is designed for 3D points without color information. We improved it to consider the color data as well. Algorithm basically applies a connected component algorithm in the spherical coordinate system, with the given distance metric in the slide and the adjacency decision procedure. Using this criteria, a connected component algorithm is applied and the segments in the region are found. Then among the found segments, we need to determine which one is the hand segment. For this, we utilize the observation that hand should be the biggest object in its bounding box as well as the closest object to the camera. A score is assigned to each segment to measure these two properties, and the segment with the biggest score is assumed to be hand segment. After having hand segment, we determine the 3D pointing direction. In our method, we try to find the pointing part of the hand. What do we mean by the pointing part of the hand? Well, the common thing about the pointing gesture is that significantly big part of the hand is gathered around the line in a pointing gesture. We define points around that line as pointing part of the hand. Now let me explain how do we get this pointing part of the hand. First, eigenvectors and eigenvalues of the covariance matrix of the 3D hand points are found. Since principal eigenvector gives the direction where the data is mostly dispersed, we expect our final direction estimation to be close to the principal eigenvector. This is key to our algorithm. We assume that pointing part of the hand is a collection of hand 3D points with maximum cardinality whose orientation is close to the principal eigenvector V0. This assumption makes sense since we assume V0 is close to the pointing direction and big part of the hand is gathered around the line in pointing gesture. With this assumption, the pointing part of the hand is found through finding two planes whose normals are orthogonal to V0 and whose neighborhoods contain the largest amount of 3D hand points. Finally, the effect of the sensor noise on the final prediction is investigated. Namely, a bound of errors of the principal eigenvalue and eigenvector is found. We approximate the covariance matrix of the noisy data as an equation 2, where the sigma is the true covariance and ns is the covariance of the noise, which is assumed to be a multiple of the identity matrix. Then we use Weyl inequality to find the bound on principal eigenvalue error, and there is a Cohen equation for the error on the principal eigenvector. The success of the pointing gesture classifier is investigated on the pointing gesture dataset, which is divided into training, validation, and test datasets. The number of images in each set are given in the table. As it can be seen, we achieve a 94.0 accuracy in the test dataset. Our 3D pointing direction dataset includes images with varying hand distances to the camera. We group each image depending on the hand distances into the three groups: close, far, and distant. In the first table, you can see the number of images in each of these three groups. Our procedure on the experiment is as follows. We classified a direction estimation as accurate if the angle between the estimated direction and the ground truth direction is less than a threshold. We used three different thresholds: 10 degrees, 15 degrees, and 20 degrees, results of which given in the middle table. As it can be seen, we achieve a 83.7% accuracy for the 20 degrees threshold. We also investigated the accuracy rates for the different distance groups. We also ran our 3D pointing direction algorithm on the publicly available IPO dataset. This dataset includes images where the hand's distance to the camera is less than 1.5 meter. In the table, our results, as well as the results of an existing algorithm, is given on the dataset. As it can be seen, the results of both algorithms are close, but the existing algorithm performs slightly better than our method. But it should also be noted that the existing algorithm only works for the images where the hand's distance to the camera is small. Let me conclude my speech with the final remarks. Our three main contributions in the paper are a new 3D pointing direction estimation method with the least amount of assumptions, a sensor noise analysis on the final predicted direction, and two publicly available datasets that can be used as a benchmark for future studies. As a future work to this paper, a human-guided object learning may be built on top of the presented method, and also the temporality of the incoming sensor data may be used to improve the accuracy. Finally, I want to thank Özgür Erkent for his comments on the methods and Mehmet Yasin Özkan for his contributions during the labeling of the datasets. Thank you for listening to me.